Study with Steph, cause she's the best. She's gonna help you get your CTS, yeah.
Ain't nothing can keep me down.
Stephanie.
Hey everybody, welcome back to Study with Steph. I'm Steph, and I am working to get my CTS. Today we are discussing Chapter 10 of the CTS Handbook, which is on wireless radio systems. And I have with me Pete Putman, President of rAVe Consulting. Welcome.
How you doing?
So I had you on here because you are the wireless radio systems guy. I've heard many people at rAVe, and a few people have told me that you would be really great at helping me out with this chapter. You taught a class about it at InfoComm a few years ago, and you taught it multiple times. So thanks for being here.
Oh, my pleasure.
So a few things that I just wanted us to make sure that we covered today was kind of three things. I wanted to talk about the basics of radio waves, kind of how they work, what's going on with them, and then what's required to send and receive signals, and then why the right antenna setup matters, and what can go wrong on a job if you somehow mess that up.
Okay, that's a good start.
So do you want to start with just talking generally about radio waves?
We can do that.
Okay.
Just a little bit of background. I've had have had an amateur radio license for 51 years. So I got into this when I was very young. Actually had pirate radio stations in high school. Got thrown out of college for operating one. But it's the best way to learn on the job, right?
You're right.
And at one time in a previous residence, I had a 65-foot crank up tower with 11 antennas on it. And over the years, I've experimented with bouncing signals off the moon, off of satellites, off of the Aurora Borealis. I've built homemade radio systems and taken them in backpacks to the top of mountains with portable antennas to operate. Had a lot of fun with it over the years, so it's kind of in my blood. But radio waves, I like to say in my class, radio waves are kind of like cattle. If you don't herd them, put a fence around them and herd them, they can cause all kinds of problems. But once you figure out where you want them to go, what you want them to do, there you can accomplish some amazing things with them. And we're at a funny inflection point now in that we depend so much on wireless, we don't even think about it anymore. And yet it seems that as the demand for wireless goes up, the knowledge base, the people out there that really understand how it works seems to be going in the opposite direction, an inverse direction. And that was really the inspiration for doing the class, was to say to people, look, this stuff's important. You can't just take it for granted. When you have trouble with it or it's not working right, or you need to design a system, you need to understand the basics and then build on the basics. Once you have the basics, the rest is easy. And as I like to joke in my class, the unit of resistance is the ohm. And notice that's very similar to the transcendental meditation ohm. There's a reason for that. And years ago, when I used to write a column for Ham Radio magazine, somebody told me in a crazy letter that the impedance of the universe was 276 ohms. I don't know where he got that number from. But there seems to be a connection between the universe and electricity and photons. So radio waves, well, all they are sine waves. A sine wave, I'm sure you're familiar with what it looks like.
Mm-hmm.
It goes up, it goes down. It's an AC signal. It has a plus and a minus to it. 1 cycle per second is one sine wave. And what happens is as you oscillate at higher frequencies, you start to hear them. And that becomes audio frequencies.
Right.
And then once you go beyond what a dog can hear, then it becomes extremely low frequencies, then low, then high frequencies, medium high frequencies, very high, extremely high, super giga high. It's the same thing. It's just oscillating faster and faster and faster. And at some point, those electrons that travel through and along the surface of a wire move to the outside of it and you'll just leap off of it. Once the frequency gets so high, they literally become photons and they just travel through the air. And that's really what radio waves are. So we can actually measure them. Nobody's come up with an ink yet that you can inject in an antenna and see what a radio wave looks like, but we can measure them. And we can measure them in meters, or we can measure them in frequency. And frequency and meters, the wavelength, the size of the wavelength is measured in meters. The frequency is measured in hertz, kilohertz, megahertz, gigahertz, terahertz, and so on. And they're inversely proportional. So as the frequency gets higher and higher and higher, the radio waves get smaller and smaller and smaller. As the frequency goes lower, the radio waves get bigger and bigger and bigger. So if you're out driving in your car and you see a really tall tower That's typically an AM radio station. Sometimes it could be a TV station with antennas on the top, but the AM radio station operating in the AM radio band has a very, very long wavelength. The radio wave, if you could see it, can be several hundred feet long coming off of the antenna. Inversely to that, or conversely to that, a signal coming from a UHF TV station can be about this big. So the antenna is very small and needs to be as high as possible to get the signal out there. So the key to understanding what kind of antenna to use, and also knowing intuitively whether an antenna will work or not, is to understand the wavelength of the frequencies that you're working at. So with something like a cell phone, well, these things are operating at extremely high microwave frequencies, so the antennas are very, very small. But something like this radio here, this is a multi-band amateur radio. This is a very inefficient antenna, but it'll operate at 144 megahertz and 430 megahertz. If you're watching channel 2 on a television, you might have seen these things. Your grandparents probably had them. Rabbit ears.
Yes.
Antennas that you pull out of the back of the TV. Well, the reason you need that is that the wavelength of a signal at channel 2 is about 6 meters. 6 times 3 roughly is 18 feet. So a full wavelength is 18 feet. So what you want to do is make sure that the antenna you use is closely matched to the wavelength of the frequencies that you're operating at, and then you get maximum energy transfer coming in and going out. And it's really that simple.
Okay. So I guess that like
a simple piece of math, by the way, if you want to figure out what the frequency and the wavelength are, if you know one or the other, is just to take, for example, if I'm operating at 50 megahertz, I divide that into 300 and I get 6 meters. Or I divide 6 meters into 300 and I get 50 megahertz. So you take the wavelength and divide it into 300 to get the frequency, and you take the frequency, divide it into 300 to get the wavelength. So that's a quick way to do it. Sometimes you wind up with fractions working at microwaves, such as with Wi-Fi bands. But that's really what the relationship is. So you probably saw the video. I don't know if you got a chance to see the video I sent you about receiving TV signals in a very remote location. Well, one of the reasons that works is that the antennas are tuned to and very resonant at the frequency. When they're resonant, when their physical length approximates about 1/2 to 1/4 of a wavelength, then you see maximum energy transfer. It's not to say you wouldn't pick up a signal with a much smaller antenna, but this is why, for example, when digital TV took off, people were buying these little panel antennas about yay big. And they're saying, well, I can't get channel 6 or channel 4 or channel 2 or channel 7. Well, they don't work very well there because they're not big enough. It's that simple.
So I guess that one of my main questions is like, how do you intuitively know what size that you're going to need? Just like time and like working with this so much?
Well, that's pretty much it. But again, you can use that formula I gave you. So if you're going to install a given antenna system and you know the frequency that you're operating at, you can divide that into 300, and then I'll tell you what the wavelength is, roughly what the wavelength is. Now, you don't typically put a full wavelength antenna anywhere because you don't need to. You need to typically put a 1/4 or a 1/2 wavelength antenna, and that'll give you plenty of energy transfer. So even though you're operating something at 6 meters, you only need a 3-meter long antenna. And you could use something smaller. So if you happen to live next door to a TV station, which could be unfortunate, there's so much energy coming in that even a paper clip is going to pick up the signal. So it doesn't matter how inefficient your antenna system is. But if you're in an area where you have very weak signals, for example, you're trying to extend the range of a wireless system, then you want to have wireless mic system or wireless video. You want to have an antenna system that is as close as possible to the desired receiving frequency to maximize the energy transfer. So again, that quickie formula dividing into 300 will give you one or the other. Okay.
So remind me again, which one means that you need a smaller antenna, and which one, like how big of a signal means that a bigger antenna, like what's the relationship again? Could you explain
Well, as
that?
you go higher in frequency, the wavelengths get smaller.
Right.
So for example, if you're using a 5 gigahertz wireless video system, and I think it was in my table there, you're talking about something, or maybe even 10 gigahertz, you're talking about something that's like 0.06 inches. I mean, you're talking about a wavelength that's that big.
Okay.
So that kind of antenna can be built right onto a circuit board. It can be etched with copper right into it, which is what makes these things work. It's actually the antenna is etched right into the circuit board.
So it's because the wavelength is small. It's
That's right.
operating at
The
such a
higher the
high
wavelength,
frequency.
higher the wavelength, the smaller the antenna. The lower the wavelength, the larger the antenna.
Okay, that makes
That's an
sense.
absolute
So,
rule.
okay. So what is something that's so low that it would need like a giant antenna? Like what's an example?
Well, for the Navy for years, decades, has been experimenting with communication with submarines all around the globe by using very low frequencies. So these are just above the range of hearing. And they have an enormous antenna farm in Wisconsin where the antennas themselves are buried and they run for miles. But this was the only way that they could communicate with submarines, say at the South Pole, North Pole, or in the South Pacific Ocean from one central location. You use these very, very low frequencies. The AM radio band, a station operating on 700 kilohertz, you'd have to divide that into 300, but you're talking about an antenna that's several hundred feet tall. And to transfer any energy efficiently. We, as a rule, are moving away from those lower frequencies to the higher frequencies, to microwaves, UHF television, things like that. We're still using some of the lower frequencies, and as a ham radio operator, we use many, many of them. And you still have shortwave broadcasting stations in different countries. They use those frequencies. And here's why. Once you get to be around 10 to 14 to 18 megahertz, the signals will transmit with equal strength or close to equal strength, daytime or nighttime. As you go lower in frequency, what happens is the signals have a certain distance that they travel in the daytime, but at night, they actually bounce off the ionosphere. So way back even in the 1930s, the FCC created something called clear channel AM radio stations, where after sunset, only one broadcaster was allowed to operate on a channel, because that channel could be heard all over the United States. So when I grew up, it was WABC in New York City. I'm not sure where you're from, but down in Charlotte, WBT, KFI in Los Angeles, these guys had the channel all to themselves. And the idea was that anywhere in the US, you could listen to these signals because they would bounce off the ionosphere. But as you start to go higher in frequency, it doesn't really matter whether it's daytime or nighttime. And as you go even higher still, well, the waves don't travel as far. So with this radio, if I stand at ground level and I'm talking to somebody, my distance is about the curvature of the earth, about 8 to 10 miles. That's it. And at that point, the radio waves just go straight as an arrow and zoom off into space.
Okay.
So now we're talking about at higher frequencies using radio stations and systems on tops of mountains, on tops of buildings, even satellites. So that's another thing about radio waves. They tend to go in a straight line, but at lower frequencies, they can be affected by different parts of the atmosphere. Another example is at night, or for example, we're seeing these storms come through. Sometimes when a storm comes through and you have a temperature inversion, so you will awaken in the morning and there'll be fog out there. What does that mean? Well, that means that you have a layer of cold air close to the ground trapped by a layer of warm air above it. Well, when that happens, it actually creates what's like an air duct, like an air conditioning duct, and a radio wave will get in there and at the right frequency and bounce back and forth, sometimes up to 1,000 miles before it comes out again. And the next thing you know, you're in Florida watching TV stations in Texas, or you're in Maine watching TV stations in Florida. And this is a pretty common occurrence in the fall. So it's just nothing you really need to remember, just that radio waves can do funny things that way.
Yeah, that makes sense. So when you said that the Navy is using these antennas at a really low frequency, what's to keep anything from interfering? Because you said it's easier for stuff to interfere when you're working at that lower frequency.
Well, noise, primarily noise. So lightning, static, electric motors, vacuum cleaners, appliances, computer power supplies, switching power supplies. These things can all create interference.
Is that because they operate at similar frequencies?
Well, they're giving off their motors. I mean, they're sparking, they're creating small amounts of electromagnetic energy, and that electromagnetic energy can create noise, which interferes with the desired communication. If you're familiar with what's called the Green Bank Observatory in West Virginia, this is a very small town where there's very sensitive radio astronomy satellite dishes, and nobody's allowed to have cell phones in there who lives in that area. And they have very slow speed internet because they don't want any noise or outside interference to block any signals that are being picked up by these dishes. They've been there for years. So it's a very, very interesting area. I mean, imagine an area where you live where you don't have Wi-Fi, you don't have a cell phone, you have cable TV, you know, if you get anything. It's actually very clean electromagnetically. There's very little in the spectrum because those dishes are aimed towards distant parts of the universe out into space to try to pick up any weak signals that might be coming in. So there are people that are very much attuned to interference. And of course, there are ways that you can mitigate interference. There are ways you can deal with it and block it if you know what you're doing.
Right. That makes sense. What are a few ways to do that, to block it or keep it from interfering?
Well, one of the simplest ways to do it is to use something called the filter. Filters are used in all kinds of equipment. Some of the best wireless microphone systems out there have filters in them. All a filter is really is a combination of electronic components that will either pass or block a signal at a certain frequency. So for example, if you want to be able to use a wireless mic system and you don't really care about any of the signals below, say, 500 megahertz, then you would install what's called a high pass filter. And if you could see this on a piece of test equipment like a spectrum analyzer, all the signals below 500 megahertz would look like they fell off a cliff.
They just disappear. Yeah.
They disappear completely. Conversely, if you want to be able to watch channels 7 through 13, you don't want anything above that, then you have a low pass filter. So everything above, say, 230, 240 megahertz, again, just falls off a cliff. You don't see it. It's completely blocked. Good example of this, in the most recent reallocation of TV channel frequencies, everything above channel 37, which is reserved for radio astronomy, has been reallocated to other services. Well, T-Mobile operates wireless telephone nodes and mobile phone nodes just above that. And if you're receiving over-the-air television like I do with an antenna, and you're near one of those nodes, you can see that on a spectrum analyzer. You can see this very intense, very strong pulsing of signals. And what you do is you install this little filter, and that filter basically cuts off all the signals above channel 37. You won't see anything at all. It's just gone.
Why would you want to do that?
Well, because if that signal is so strong from T-Mobile, it might interfere with what you actually want to watch on a UHF TV channel. It might cause it to drop out. So once you put that filter in, no more dropout. And then you can combine them. So you can actually create what are called active filters. They're digitally tuned. And you can, for really, really good, say, wireless mic systems, the top of the line wireless mic systems, these things actually can change frequency and they can block everything above and below the frequencies that you're operating on. So you never hear it, you never see it, you never hear it. They're bulletproof.
Okay, that makes sense. Can I ask you a few questions about like regulation for a few minutes? So basically it's the International Telecommunications Union that controls,
based in Switzerland, correct.
So they control regulation of radio waves all over the world.
Well, they don't control them. The ITU is comprised of a bunch of member bodies. Each nation has its own telecommunications regulatory authority. In our country, it's the Federal Communications Commission, which has been around since 1934. And we're all member bodies of that. So really what the ITU does is not necessarily say you can or cannot use these bands for certain types of operation. What it does is it coordinates among different countries to say, which band should we set aside for emergency communications? Which one should we set aside for television broadcasts? Which one should we set aside for radio broadcasts? Which one should we set aside for Wi-Fi? And for a whole new bunch of wireless products we haven't even seen yet. So really what happens is the regulation takes place on the national level. Now, to give you an idea of how this can get tricky, typically in the United States, the FCC governs, they regulate which bands are used, which frequency bands are used for different services. And we coordinate with Mexico and Canada because we obviously have municipalities and cities on the borders with Canada and with Mexico. So when we realigned our digital TV spectrum, which is now channels 14 through 36, and we auctioned off channels 37 and up, we had to move a whole bunch of stations around. We had to play musical chairs.
Right.
We don't have a lot of open frequencies left. So we have come up with other ways to accommodate those people using a multiplexing of signals. But at the same time, we had to talk to Canada and say, well, this station in Toronto operates on channel 9, but we just moved a station in Rochester across Lake Ontario to channel 9. So you can design your antenna so that very little of your signal heads north across the lake to Ontario, and most of it stays south of Rochester, east and west in New York State. So there was quite a bit of that negotiating that had to go on
Right.
when it wasn't just a question of saying, all right, guys, we're kicking you off channels 38 and above, and we're going to move you to other channels. We had to talk to Mexico. We had to talk to Canada and say, we're going to be moving these guys off these channels, and we want to make sure we're not interfering with channels that you're using. Similarly, in Canada and Mexico, they may not have vacated those same UHF channels, so they need to be aware of new operations. So for example, a channel 40 in Canada that's transmitting near the border may find they're on the same frequency with a new T-Mobile mobile service that's operating on channel 40 in the US. So there's a lot of this back and forth coordination between the different bodies. What the ITU does is the ITU will convene, get people together, and then say, we propose to set aside channels in the 60 gigahertz band, the millimeter wave band, for 5G. And these are the channels that we'd like to use. So they try to get as many member countries to sign on and agree to do that, so we're not creating interference with each other. Now,
So if there were two, okay,
go
sorry.
ahead.
If there were two channels that were like accidentally operating on the same frequency because they hadn't talked to each other, what would happen? Would they just cancel each other out and there'd be nothing?
Well, we had that problem. Now, remember before I mentioned to you that atmospheric conditions can cause signals to travel a lot further than was intended.
Right.
We had a situation a few years ago after 2009, after the first reallocation of channels, where channels 14 and 15 in the UHF TV band are also used by public safety agencies in some areas where there are no TV channels allocated. So for example, an ambulance dispatcher, police cars, fire departments, other public safety agencies. Well, when we had this condition where we had a temperature inversion along the East Coast, and what this is, it affects the troposphere, the part of the atmosphere, the troposphere. The signals were bouncing and coming back down, so that a public safety agency in Camden, New Jersey, not far from me, was being wiped out by a TV station on channel 14 in Boston. Only because of that condition. When that condition didn't exist and we didn't have a temperature inversion, everything was fine. So you not only have to say, well, okay, Boston's quite a distance from Camden. It's highly unlikely they'll interfere with each other.
Right.
You need experienced people to say, yes, but certain times of the year, for example, we just had a hurricane blow through here. Sometimes a hurricane can create this tropospheric ducting. Sometimes you can get something called sporadic ionization of the E layer of the atmosphere, which can cause even lower frequency signals to be picked up. So somebody in California is watching a TV station from Florida on channel 6, like, wow, where'd they come from? So, so the point here is that the experienced people, and my fear is that there aren't as many of them as there used to be. And by the way, many of them were ham radio operators. That's where they learned this stuff. We look at these allocations and say, well, that's pretty good what you did there, separating these stations, but you also have to allow for certain types of atmospheric conditions throughout the year. You certainly wouldn't want an ambulance not to hear from a dispatcher if somebody's life is on the line because a TV station in some part of the East Coast is interfering with it. So that whole has to be taken into consideration.
That makes sense. Can I take a step back again and ask
you,
so there are three terms that I tend to use interchangeably, and I know that that is incorrect. So, and I know a lot of other people do it too. So radio, wireless, and RF, like especially in the AV industry, those are kind of used as like three interchangeable terms. So can you just kind of lay down the distinct differences between the three for me?
Well, RF is easy. RF just stands for radio frequency.
Right.
So you can have RF energy, radio frequency energy. That's just basically radio waves traveling. And that's sort of a catch-all term. In fact, all three are sort of catch-all terms that we use.
But the RF signal doesn't have to be carried by radio waves, right?
Well, an RF signal is radio waves. Yes.
Okay.
If it's a radio frequency signal, it is a radio signal.
Okay.
And it can travel over wire, such as coaxial cable or balanced line wire, or it can just travel through the air from an antenna. But it pertains to the fact that it is a signal that is oscillating at a radio frequency, which is generally considered to be everything above, I think it's 30 kilohertz, up to visible light.
And so wireless, it can be a type of RF signal, but like you said, RF signals can be carried over wire. But if it's wireless, it's obviously not carried over.
Yeah,
a
a
coaxial or
wireless
anything.
signal, a wireless signal is something that came from an antenna and was picked up by an antenna. But a radio frequency signal can travel through an antenna, or it can travel over a piece of cable. It can do either
Okay.
one. So wireless would be a sort of a subset of that.
So when people talk about radio in general, like that is like that's not like, they might not necessarily be talking about RF or wireless. They're talking about like radio itself.
Yeah, you'll hear somebody saying that we want to set up a 2.4 gig radio, or we want to set up a 5 gig radio, or they'll talk about on the news that the Afghanistan radio, it's just sort of a catch-all term. It implies some form of communication, which could be wire or wireless. So it's really to be more accurate, we talk about a wireless access point, we talk about wireless routers, we talk about wireless, well, we don't have wireless switches per se, but you have a transmitter or a receiver, or you have a transceiver, which means it can transmit and receive. It can do
And
both.
receive. Yeah.
So this is a transceiver. Okay. All this is what this is doing. I push to talk, and when I let it go, it's now a receiver. A TV station and an FM station, that's a transmitter.
It's a transmitter. Yeah.
This guy
So
over
then
here,
so then your
this
TV,
guy over here, that's a receiver.
so then your TV at your house that's getting your TV channels is your receiver.
That's a receiver, correct. That is a television receiver. Although nowadays you have smart TVs with internet built into them.
Right.
So they have Wi-Fi radios in them.
Yeah.
Yeah, they're actually, they can work, they can work as a transceiver because they can send or receive Wi-Fi signals. But the basic function of a TV, you're absolutely correct, is as just a receiver.
Do you mind talking to me about a few different types of antennas and why choosing the right one matters?
Sure. You basically have, let's break it down. You have 3 kinds of antennas.
Okay.
So you have the omnidirectional antenna, which will pick up signals
from all directions,
consistently from all directions. They don't all do that. If you look, you can actually plot the pattern of these things on a graph. You can see it on graph paper, but in theory, that it doesn't care where the signal's coming from. It will pick up signals from anywhere.
Okay.
But that's not a very efficient antenna if most of your signals are coming from one direction. So it doesn't have a lot of
because they travel in a straight line, right? So having one that goes from all, even when you can pinpoint where it's coming from, that doesn't seem like it'd be the best option.
Correct. Yeah. So that would be very inefficient. If you noticed from the video I showed you, I'm in a very remote area of Vermont. I'm trying to pick up TV stations that are 54 miles away, blocked by a hill. So an omnidirectional antenna is not going to do me any good there, because there's nothing for maybe out of 360 degrees in a circle, there's probably nothing within 330 degrees that I want to watch.
Sure.
So that antenna has what's called very low gain. It's just basically a dumb antenna. So what we can do is we can then go to a bidirectional antenna. A bidirectional antenna basically has a reception pattern that looks like a figure 8 off of each side. So if we have, and I'm going to do this with pencils. So if this is our bidirectional antenna, and this is a function of the frequency of the antenna, this approximates the desired wavelength, we have a pattern that looks like a figure 8 here, and a pattern that looks like a figure 8 here.
Okay.
So one off the top, one off the bottom. That's called a dipole. That's a very, very basic antenna, one of the simplest antenna designs. And in fact, in the industry, when we talk about the gain of an antenna, we talk about the gain over what's called an isotropic dipole, which is basically an imaginary antenna in space, not near anything.
Okay.
So we measure gain over that. That's a perfect antenna, or a theoretical antenna.
Okay.
So your rabbit ears, believe it or not, your rabbit ears, that's a form of a dipole. They don't look like it. They come up like a V, but that's a form of a dipole.
But they're technically like 2 right here when you don't
but they can
mess with
they can be bent in a V shape. They can, be put in a corner. But all TV antennas, and by the way, more advanced antennas that do have a lot of gain and are directional, the physical element that's actually connected is still a dipole. So we use that everywhere.
Okay.
Now, in the case of wanting to get signals from one direction, then we have an antenna that is a unidirectional, not omni, but uni, which means one direction.
Right.
And the most common one of those is what's called a beam, a BEAM antenna, but it was invented by a Japanese engineer called Dr. Yagi Uda back in the 1920s. So in the ham radio world, we call them Yagis. Remember, that's a lot like yogi, which is a yoga, which is Om. So we're back to that whole meditation thing.
Right.
But a Yagi antenna, you'll know when you see them, they look like they have, for example, a curved or multiple elements in the back, and they seem to be pointing like an arrow. And they have
Okay.
multiple elements in the front. Well, the arrow actually points backwards from the signal. That's the back of the antenna. That's the reflector. Then you only have these other elements in front called the driven elements, or the directors rather. And then you have that little dipole. That's it. So it's the same thing as if you were talking to somebody and they couldn't hear you, or you put a speaker out and they couldn't hear you, and you put a big bowl behind the speaker. All of a sudden they can now hear you because it's gathering all the audio and it's reflecting it this way. So the Yagi antenna works exactly the same way. It takes the radio signals that are being emitted or received, and it gives them a directional component.
So can I ask about RF cables now? Like, what are a few different cable types that you think I should know and be able to identify?
Sure. Well, in our industry, the most common type of cable we're going to use is coaxial cable.
Mm-hmm.
Coaxial cable got its name because it has a center conductor, has an insulator, and it has a shield that wraps around it, a braid of some kind. And it can also have a aluminum shield or something on that. And then it has an outer jacket to protect it. That's where it gets the term coaxial. So everything is concentric on an axial basis. One thing that's kind of interesting to note, radio waves, because they oscillate positive and negative, work best with what's called balanced wire. It just looks like two wires that are evenly spaced. And in fact, back in the days when your grandparents and your great-grandparents watched TV, that's what they used. It was called twin lead. There's this brown wire that they ran from the antenna down the side of the house through a window or whatever and into the TV. That's actually the most efficient and least lossy type of cable there is, but we hardly ever see it because the minute you get it near anything metallic, like a gutter or pipe or anything, it detunes it. So not practical. Yeah.
Right.
But I mean, in an ideal world, that would be the best antenna to use. And in fact, if you go online and you look at pictures of old radio stations going back to Marconi's days and all, you will see open wire line coming out of these transmitters, evenly spaced with ceramic insulators going all the way up to a big dipole antenna strung between two towers. That's the best way to do it.
Gotcha.
Very impractical, but it's very impractical at these frequencies. It works great for lower stuff. So back during the war, World War II, a company called American Amphenol, developed something called coaxial cable because they were putting radios in ships. Well, what are ships made out of? Metal. So you can't use open wire line. So they came up with coaxial cable. And coaxial cable comes in many different sizes. You can get really tiny coaxial cable. You can get big fat pieces of it at very high frequencies, such as you'd see in a UHF TV stations. It's actually plumbing. There's no wire. The radio waves just travel through the plumbing. The plumbing is actually electrically resonant. It's fun to watch them assemble these things. They're called waveguides. So in our industry, we use primarily coaxial cables. So for doing multi-channel video distribution, if you're using wireless microphones, we're using wireless video, we're doing baseband video, we're going to use coaxial cable. And it comes with two impedances. Impedance is the AC form of resistance. It's also measured in ohms. It's dependent on two different things. Capacitive and inductive reactance, which is way beyond the scope of the CTS exam. There's a formula to determine that. But when those two things balance out, that's the impedance of the cable. So the most common impedances are 50 ohms and 72 ohms, sometimes 75 ohms. So cable TV, RG6 is a common cable, RG59. Those are 72, 75 ohm cables. RG8, RG58, Mini 8, some of the more elaborate Belden 9913 and all, those are 50 ohm cables. So typically for multi-channel video distribution, because the cable TV networks use it, we use 72 and 75 ohm cables. Well, you may have heard of something called a balun. A balun is something that takes balanced wire and converts it to unbalanced. So balanced is 300 ohms and unbalanced is 72 to 75 ohms. So there is a mathematical relationship between those. It's roughly 1/4 of 300. 50 ohm cable is used primarily for transmitting. So if you're putting a wireless mic system in and you're running cables to all the antennas, that's going to be 50 ohm cable. And they'll probably either be RG58 or RG8 or RG8X, or I can't keep track of them all, M440. There's so many of them out there.
Got it.
And that's pretty much the two that you'll work with. As a general rule, the larger the cable, the lower the losses over long distances.
Yeah, very cool. I think those were all the questions that I had prepared for you. I guess the last thing I wanted to ask you is, since I'm studying for this and I'm coming at it from a different like from a different way than most people are. Like most people are coming at this already integrators taking the CTS test, and I'm coming at this knowing journalism but not much about like AV. So do you have any advice for me as I'm studying and I'm trying to kind of come at this from a different perspective?
Well, as I've often said, having taught at Infocom for over 2 decades, that the best people to take these tests are the people who have been working in the industry for a long time, because the concepts aren't so abstract, they're more concrete. They're like, oh yeah, I've worked with that, or I've built one of those, or I've encountered that problem. So sure, I know the answer to that.
Right.
Which is, again, one of the problems with taking a test like this, is that it's a chicken and egg thing. You know, it's, well, which do you have to have first? Obviously, if you have more experience, you're going to do better on the test.
Sure.
But, you know, to try to take the test, if somebody's going to hire you, they might want you to pass the test so that you can gain the experience you need.
Right.
That's what makes it difficult. So it's kind of like when you were in high school and you had a cram for an exam in French. I don't know if you took a foreign language, and if you did, you probably don't speak it now. But it's the same sort of thing. You have to cram your head with a lot of knowledge, knowing that over time you may lose most of it because you're not using it. So to me, the CTS is just it's an introduction to these concepts, and hopefully they're not getting too deep on the RF. In fact, I think at one point I probably came up with a few of the questions. I think I was on the board a number of years ago and wrote a bunch of the questions and the answers for the CTS on RF and wireless. I wouldn't expect most people to remember most of this stuff unless they're actually out there crimping connectors, running cables, setting up antennas, you know, trying to configure a wireless system, a radio system, a cable TV system, whatever they want to do. I wouldn't expect them to remember much of this because, again, it's abstract thinking.
Well, Pete, thank you. Thank you so much again. I really appreciate it. This has been another episode of Study with Steph. All the episodes can be found on iTunes, Spotify, pretty much anywhere where you listen to or watch podcasts, YouTube as well. And I will see you guys next time. Bye.
Study with Steph, 'cause she's the best. She's gonna help you get your CTS, yeah.
Ain't nothing can keep me down.
Stephanie.